As we get started, I just want to acknowledge Ferris Ward and also Marie Henderson, who are the two early career individuals who are helping out with this breakout session. And breakout session number 1, as I mentioned in the plenary, is about historical lessons learned for pre-mission activities. As I try to explain, what we're looking for are insights based on what was done in Apollo, but also with Mars exploration, ISS, all sorts of exploration in the past. What sort of activities, tools, infrastructure are helpful and needed in the preparation for a mission to really enable a science team to do its work later on during the mission. So let me advance slides here. Oops. So again, just to remind you on the rules of engagement, let's try to have a lively conversation here. I think many of us have sort of ideas, and we really want to capture those ideas. Feel free to raise your hand or somehow get my attention or Ferris's attention if you want to speak. Otherwise, you can post to the chat. Ferris and Marie, I'm going to rely on you to give me situational awareness on the chat, since the interface here is a little daunting for me, and having to monitor that and talk at the same time. So if you have a question, have something to say, please get our attention. Otherwise, you can type to the chat. Let's see. So let's get to this. So as I mentioned, Breakout 1 is what we're here doing. Just so you're aware, Breakout 2 has sort of a parallel set of questions. And so if you're wondering sort of where your question might fit or how they might relate, hopefully this will help with that. And as I mentioned before, you can hop back and forth between breakouts. You won't hurt feelings if you do that. So some leading questions just to get the conversation started. These are the same that were posted to the LSSW website in the run-up to this meeting. So what traverse planning strategies, for example, for robotic missions with time delay, so Mars, would be amenable to human exploration? What traverse planning strategies for Apollo work best? What lessons learned can we leverage from Apollo on training and those sorts of things? And again, what I think is probably the most important bullet point here are what are the sort of ways that we can best integrate engineering, mission operations, and science to best prepare the science operation team to do their job in real time when the mission's going on. So just a few starting thoughts. As I listened to the talks today, it seemed like many of the presentations and many of sort of the question and answer discussions we had some common messages in this vein. And among them were the need to train the crew in the field, the need to do mission simulations with the entire team, including those that are the scientists, and then the need to integrate science and engineering, ideally as early as possible. So just to get things started, I have a couple questions just to spur some discussion. What specific sort of training, simulation, and integration activities do we think NASA should start today? And also, what tools, facilities, personnel, infrastructure, what have you, would be needed to realize these efforts in the near term? So take it away.
This is Fred from JPL.
Hi, Fred.
I hate to be the Mars person speaking in the Lunar talk right away, but I can tell you that we do numerous simulations with as good as data we can. That includes, though it may seem strange, but actual field work on the Earth at different locations in analog Mars environments with well, as close as we can get to flight-like equipment, and do real-time testing of, like moving the rover and taking images and doing commanding as best we can, and trying to get the tools in the hands of the science team and the engineers to work through issues and problems. Sometimes it's just coordination. Sometimes it's, what products are available, and trying to just like work on the workflow and also see what the data sets are available and get people used to the tools, right? Because our tools evolve every mission, partly because you have years that separate missions, but we always try to build on the past, but also just go with new technologies. For example, 2020, where everything is pushed to the cloud, everyone's distributed, and that was going to be true. Well, more true now because of COVID. but would always eventually be true that our science team disperses out into the quote unquote the wilderness, but international, right? We have partners all around the world, but they have to operate in the same time schedules and have tools that they can actually access in real time in terms of planning. So I think analog missions, and then also using data that was from surface missions, in our case for Mars, or from the moon where possible, is really useful.
Yeah, those are great insights. Have you found that in the run up to like the Perseverance mission, that there's been a lot of change in sort of how operations have been done from, say, Curiosity and MSL before that?
I would say generally, like in terms of meeting planning, I would say no, we've got it pretty down pat in terms of some science discussion up front that then gets shuffled off into instrument teams to develop like the refined targeting. It's like, oh, science, I want to look at rock number 27. Okay, which instruments? And then okay, like say Mastcam Z, how what are the pointing for that instrument, and is it right? And then looping through the science team saying, yep, that's it. And then doing all the the detailed work of going forward, and then all the engineering things like power and communications, and make sure that is balanced with the science request. I don't think that's changed at all. The tools, night and day. I mean, we went from things that were very like engineering and command line and custom and unique to operations, the tools that now are kind of broadly spread out and shared with everyone. Just speaking from a mapping perspective, it went from no one was in charge of mapping, but a lot of maps were made in different bases, and that includes both engineering and science, to the engineering and science team have the same base map. We work with the same set of coordinates. We can translate between instrument coordinates to mapping Cartesian coordinates and vice versa, and we can all share that data and understand where we are all the time. So and I think it's just leveraging that ability. And then again, these tools are web-based, they're distributed, so we can pull in team members from far away. And they talk about this back room or this physical location, but it doesn't have to be physical. It can be virtual and distributed, like we are today, right? There's really not much difference, and we've been kind of doing remote ops like that for quite a long time.
Yeah, that's a really good point about being remote. Was someone going to say something?
Sorry, Jose. Lauren, I
Yes,
was just
please.
Butting in, but I realized I should have raised my hand, so I apologize.
Oh, no worries.
To your last question for Fred about the change in operational styles between Curiosity and Perseverance, I think one thing that we might have seen change over the years or over these missions is the amount of pre-canned activities. So MSL, we have the ability to really respond, a lot of come in that day, what new data do you see, and how does that affect the activities that are going into the plan that day? But the more complex the activities will be, the more complex the instruments are, that you're reserving certain time on a certain day for those things. And so it's a little bit, less input in response to real-time observations and more, knowing where this is heading. And so I feel like that might be relevant for thinking about surface operations through Artemis.
Yeah, thanks, Lauren.
Right,
see, Ferris and Marie, are there people with hands up? I can't see.
There are 3 hands up right now. So
okay.
Let's go with Dean Epler. You're first on my screen here.
Excellent. Thank you.
Well, this is going to sound like but it really is the biggest thing we need right now.
Hey, Dean, I'm having a lot of trouble hearing you. There's a lot of background noise. Maybe you're outside in the wind.
Yeah.
And it's kind of.
How about now?
Yeah, that's better.
Okay, I just got to get closer to the screen. This is going to sound like a little bit of a flippant answer, but the 2 things I think we need most are money and management priority. If the management signs up to this, all of the stuff we're talking about here as being critical, it'll get done. The problem is, the early parts of this sort of thing, people are more interested in engineering, smoke and fire, and then they sort of tend to add this stuff on late. That certainly is what happened in Apollo. And a lot of what, the aggregate group of us that were working sort of 2010 to 2016 when I retired, we're trying to do that management thing, and I think we got a pretty good, pretty good way along. But if we can get, the powers that be to say, yeah, this is important, let's get going, we'll get it done. But if you can't get management, for instance, to send your crews out in the field to train, and they never get trained, because you're certainly not going to train this virtually. And you're not going to train it in the back lot at Johnson Space Center, because the rocks have to be important. So that's kind of my input on that.
Yeah, thanks, Dean. Yeah, it's always the money and the politics are really key things to have your ducks in the row there. Anyone else have their hand up, Ferris? I'm sure there are.
Yes, there are. Let's go with Jen Heldman.
Okay, thanks. So yeah, first of all, I agree completely with what Dean just said, and it's the money and the management that needs to make this happen. And so that's the impetus for making this a critical part, because this is what we don't want to get cut, right, when budget and schedule start compressing things. But my actual question was, when Fred was talking about the distributed for the Mars cases, but COVID and whatever else happens. So I'm thinking about the differences between how we did it for Apollo and today, right? And so today we have a much broader segment of the community that's participating in our science work, which is fantastic. But that also has some other limitations. And so one of the things that we've figured out through the course of doing more online meetings is that you can often get more participation from people who couldn't necessarily travel. I can't go for 2 weeks. I can't go for 3 months to JPL and work on a Mars mission. I can't be on travel for that long because you have other responsibilities and work duties and family duties and that sort of thing. So when Fred was talking about the distributed science team, I actually wanted to ask Ferris to talk, because part of his research at MIT is developing distributed tools to enable science operations. And so maybe one of the things we can talk about is how, potential ideas for how science ops would happen in the future, and taking advantage of these new technologies that might be, working well with the community as it is today, and just to explore that space.
Yeah, I think that's a great idea. So Ferris, what can you share with us?
Sure. So I can actually do a little spiel on our research here at MIT as part of the resource project. So there is a system that we affectionately refer to as the virtual mission control and / mission simulation system. And what this in effect allows you to do is run mission control operations in VR. And this is something that we've seen some parts of on small scales, as a lot of employees, a lot of science teams have shifted to being online only because of the pandemic and all these work-related closures, and seeing what exactly can be done without being in a laboratory, in an office, in physical meetings. And as we look forward, as we sort of further develop this technology and look toward deploying it, we get into what kind of additional science can be done, including, a great add-on for people who cannot travel, right, is people who cannot go to space. Not every single person, not every single scientist will be able to go to the moon or go to Mars, but there is still really valuable geologic science that can be done in both these places. So in effect, how do we put more people on the surface without literally putting more people on the surface? And there is a great interplay here of how these AR and VR systems work together. So there are, of course, some pluses and minuses to using either of them. But in effect, what you are enabled to do is have a science team on the moon, so several astronauts, perhaps a astronaut scientist, that sort of thing, as we have seen earlier today. That's become really important, and it was one of the more important things that allowed Apollo 17 to be successful, well, as successful as it was scientifically. We have these science teams in the environment and have separate remote science teams on Earth. And the science team that is on some extraterrestrial environment is using some AR system, and the science team on Earth is using a VR system. And in effect, they are co-located. They can see each other and they can see the environment. So with some kind of potentially LiDAR or photogrammetric mapped interface where everyone can see everything, and that greatly enhances potentially the amount of science that can be done, because it's not just asking someone, what do you see? Can you report back your findings? Can you look over here? I think there may be some interesting geologic artifacts over here based on some orbit data that we have, or some science data that we have, such as free water or some kind of hydration, any kind of data like that. A scientist on Earth can actually themselves walk over there and do a deeper investigation to a certain degree, because they're not actually on the surface. So this is a sort of completely new paradigm for science tools that is sort of really ready and really rich when we start deploying them.
Yeah, and one of the things that I really like about this potential is the visualization of the data, which we need regardless of where we're sitting too, right? Because we're going to have handheld instruments, and I've got a near infrared spectrometer, and in real time, it's not as useful for me to see the individual spectra, but you give me a heat map that colorizes where the water band depths are, and that's overlaying on the topography map, and now I can see exactly, like, the crest of the hill is dry, but if I go in this little depression, it's wet. And so you can see that, that's just an example I made up, but you can see the data in a meaningful way quicker and in context. And so just having these sorts of advanced tools for the science ops, something we can maybe think about.
Great. Thanks for the question, Jen, and thanks for sharing that, Ferris. What I'm hearing so far, and I typed something up here that I hope captures that well, is that what we need is tool development of various sorts, to enable participation, to work with any specific instrumentation deployed. That gets back to sort of this notion of increasing technology requires tools to keep up with it, and visualization and interaction with data. So it seems like that's maybe one of the top things that maybe this group would suggest needs really to be focused on tool development. Who else has a hand up? Yeah, please.
Excuse me, I didn't mean to interrupt.
Oh, no worries.
It seems the best way to tightly focus on tool development, when we know exactly what the landing site or site is going to be, when we know the specific science questions that we're going to be addressing. For instance, in the example of Schrödinger, there are at least 5 different high priority science concepts that can be tested at Schrödinger Basin. Once we know what the place is and the questions, then we can select a high fidelity analog site or sites. And at that point, that's when the selection of the absolute right tool will come in. And for instance, on Apollo 16, we had some decisions on which was the better tool for the question, the gravity method or seismic method. And we get different data and perfectly valuable in both cases. So perhaps the sequence would be to identify which problems we need to tackle and what the best tools are to do it, and do that with the astronauts, with the tool developers, the scientists at a really high fidelity simulation site. Perhaps that would be a way to structure the response to the question.
So yeah, I think that's important. I think what you're saying is to really get the scientists involved with planning up, very soon, including things like picking sites and the science that's done there. Anyone else?
And picking the tools, though.
The tools, yes.
Specific to the instruments.
Absolutely. Anyone with a hand up? I can't seem to see the hands.
I can see Catherine Logan with a hand up.
All right.
Yes, can you hear me okay?
I can.
All right, thank you. I'm a newbie, kind of, to this. I'm a retired engineer from Georgia Tech and Virginia Tech, and I'm also the retired Virginia Tech Langley professor from the National Institute of Aerospace. And I had my research laboratory actually inside Langley Research Center with my graduate students. And this meeting to me has been kind of like drinking from a fire hose, because as an engineer, I see many opportunities here for interactions with the scientists. And my disciplinary background is materials engineering. And at Langley, I developed a technology to build habitats using regolith, lunar regolith. And so from my perspective, as far as implementing science into the habitat technology, I, of course, used the lunar regolith, and the chemistry was extremely important. And the lunar regolith, of course, is varying a great deal in chemistry. And I've forgotten the name, but the geophysical presentation was really good because it provided basic information that I could use as an engineer to develop the technology to build the habitats. And so I strongly encourage the interactions, and I call it interdisciplinary. I was instrumental in initiating the interdisciplinary interactions with smart materials. And so I'm familiar with that, and strategic planning of technical interactions with the scientists and maximizing the effectiveness of the collaborations. And it is extremely important to do that, to maximize the interdisciplinary interactions between the scientists and the engineers in order to make use of the information coming from all of these planetary adventures, because we have gotten so much information from Apollo, and now the Perseverance Mars information is coming out. The next step is implementation of the science. So we need to have engineers involved in all of this.
Yes, absolutely. So let's see, who's next? I think we want to hear from, I think Ernie has your hand. You have your hand up?
Yeah, Jose. Good to see you again.
Yeah, good seeing you.
Yeah. So I think your question basically was, what can we do kind of right now in the run up to things, right? And I think one important thing we need to keep in mind is that there's not just scientists, there's not just engineers. Scientists, there's engineers, there's operations folks, who's both the flight controllers and the crew. And if we want to go a fourth area, there's actually also the management. So within all of these integrations and things, I think we need to keep in mind, particularly the first three, but we also got to make sure we keep the management up to speed, since they're the one is going to be paying the bill and essentially making sure we have the money to do this type of thing. So there's that to begin with. And then with regards to the integration through the development here up front, I think we need to look at having the ops and the scientists tied in with the engineers as they're developing the hardware. And some of this is actually already being done. I'm sure it is. I know it is. But then also the engineers, take them out into the field with us, have them see, the difficulty of actually doing field work, field geophysics, field geology. What are the type of environments what are the obstacles we have to deal with? How did the plans change? Get the ops folks out there and see how the plans change actually from the initial plan to when we're actually in the field. So you get that kind of flavor as well. And then also have the science team and the engineers to some point but the science as well, potentially sit in with listening to ISS operations or an ISS EVA and get an idea of how operations actually take place, because it's different from the way when we go out in the field and conduct science out here on Earth, where there's going to be a lot of overhead that we're going to have to deal with as far as actual performing an EVA to begin with. So it's not just all science. They have to understand that there's a lot more to it, and there's limitations and boundaries essentially that need to be adjusted for in order to get the science done, and vice versa. Basically, also, what do scientists need, and where do they actually need to access from an ops standpoint? So I think we have that. But then the other thing I wanted to mention was something that we could do up front and get more and more elaborate with before we even get to the field with a full team is something called a paper sim, or even in maybe a little bit more high fidelity type of sim. So paper sim, maybe have a couple ops folks, a couple engineering folks, a couple scientists start sitting down and go through a simulated scenario of a traverse or a particular science objective on the moon, and look at doing that. And then you get a little bit more elaborate. Maybe you pick a specific location on the moon, specific science objective. Start looking at the tools we have, maybe actually the tools we'd want to have, things like that. And then you can build the fidelity of it up from there, essentially, and then include that out in the field where you then obviously have a higher fidelity. It's a little more expensive to do that, obviously, but you can start small and grow big. And I think some of these paper sims incrementally to developing the field work might be something we could do in a short term or in the near term, essentially. But to circle back, just keep in mind, we have multiple personnel. Everybody thinks different. It's funny, we think are saying the same thing, and we'll talk right past each other. And I've experienced in both, as you know. So you can easily talk past each other and not even realize that you did that. So to get the translation there, it's going to be very important between the teams and getting them understanding each other's perspective. So I think that's some of the things we can do right now.
Yeah, that's great input, Ernie. And it's great to hear that. We've been trying to do some of that with taking some of the engineers and the managers out in the field to do geology training. So I think that's really important to continue that sort of thing. I want to acknowledge a comment that Kaizad made to the chat about maybe engaging like the public communications and outreach face of NASA, maybe another division to probably integrate with this at some point. And then I see Barbara and Dean are having some conversation about, desert rats and how that worked to bring together all these folks that need to talk to one another. Who's next with a hand up?
We have Brian Day.
All right, Brian.
Thank you. I just first of all want to second and emphasize some of the things that Ferris said. My team's working right now with his. And in addition to being able to visualize the data being gathered essentially in situ there at the moon and be able to visualize that here on Earth, being able to add context to that with the vast store of data that we already have. One thing we have the advantage of now that we didn't have back during Apollo is the vast store of data from LRO and actually from a variety of other spacecraft. We're about to add to that with the spacecraft that are coming, so the ones that are going to be launched through Artemis 1. So one of the things that will be very useful is to be able to enhance the value of that data coming back from the field by being able to, in that VR experience, actually bring in the context of all this other data that we have available and really help the interpretation of that. But because of the vastness of that, that is going to require sophisticated and faceted search. But being able to take advantage of that, not just in, I don't want to use the pejorative term, and I'll apologize, Jen, backroom, but now we're talking about expanding that out to a virtual presence, having people come in a distributed manner, making sure that that capability is available across the board, and we add context, a greater context to the data that's coming to us from the field. And then also taking advantage of those technologies. Somebody mentioned, you know, getting this out to the public and being able to get that flow of information going the other way, because I will just emphasize that we will not have a sustained presence on the moon unless we win the hearts and minds of the American public.
Great thoughts. Thank you. Who's next? I think Dean Epler was next with a hand up.
Yeah. How do you hear me now?
I hear you great, Dean.
Okay. One of the things I think it's really important to remember, and it's a multifaceted thing. One, first is that humans are not robots, and we cannot operate a human crew like we operate a robotic crew. It just doesn't work that way. And we really do have to fall back, I think, on the philosophy that Jim Head has pushed or talked about a number of times that was prevalent in Apollo, and it was train them, trust them, and turn them loose. You know, some of the things that Noah was showing, there are a lot of discussions, but it's very rare when the discussion from the back room ends up being spoken to the guys on the lunar surface, because the last thing you want to do when you're out there is have 15 guys talking in your ear and telling you all to do different things. You know, at some point we have to recognize that when the crew members are on the moon, they're doing stuff on the moon and we're sitting back and watching. And if we don't understand that, it'll sure be true when we get to Mars, because with the time delay, there's nothing you can do in the way of real-time interaction. So I would hesitate to have us start thinking about how's the backroom team going to interact with the crew on the surface. And the answer is probably when they're out on EVA, not at all, or at a very limited level. It's afterwards to talk about what did we find out, and to talk about what do we do next, or how do we change what we were planning to do tomorrow based on what we saw today. But it's not happening real time between the back room and the guys on the ground.
Thanks, Dean. Who's next with a hand up?
Alex?
Alex.
Yeah, all right. Well, great comments. And I agree with Dean. I think one of the things that's really critical to some of the training aspects, as well as a real-time mission, is that integrated story. And I know that this workshop is highly focused on the science, but it's a big mess if you don't integrate the safety aspects, the consumable aspects, the crew fatigue aspects into a recommendation when you go into like a flight director or going into a training plan. And that's why so far our training is really built on an integrated base. And you'll hear crew from Apollo, you know, we've talked to a couple of Apollo astronauts and definitely Shuttle and Station talking about like the best approach is an integrated end-to-end training approach, which means you start at the beginning of your day like you would on the surface, and you end at the end of the day. So from suit up to doffing the suit, and making sure that you know, I tell people EVAs are like running a marathon and taking the SAT at the same time, because it's 100% physical. It's very tiring, and on the lunar surface, it's even more tiring than on ISS, and maybe with a little less hand fatigue. But it's also 100% mental, and it's mental not just from what am I doing, trying to make sure that I do it right, because everyone's counting on you, but also from a pressure, a time-consuming point, and the fact that EVAs are the riskiest thing we do in space exploration, that the crew member has the ultimate authority on controlling that risk. You know, we do launch and ascent, but really a lot of that's automated. Rendezvous, a lot of it's automated, docking, same. But when it comes to EVAs, the crew has 100% control of that risk. And so that's why it's really important that we integrate at the lower level, you know, the science EVA operations team level, that integrated story, so we can be on the same page on priorities, same page on the flexecution and the mission replanning. So yeah, and I just like to also reiterate what Ernie was saying. I thought he had some really good points. And then the distance learning, you know, we've done several great kind of flight followings on ISS distance learning. I'm going to tell that to Kelsey and Jose. I know I've met you on the field, out at the field, and Lauren out on the field before, but that's something that it would be really cool to set up is through Teams, like a distance learning on, hey, here's a real ISS EVA. Let's play it, and we can have a chat window and discussing some of the items that the flight control team are discussing and what they're not, yeah, so that I just wanted to express those things. And I really love the fact that people are talking about EVAs. You're not going to be able to plan them to the detail on the lunar surface like ISS and shuttle. And I would actually spin that just a little and say, you're going to want to plan them pretty detailed. But you're going to want to allow for the flexibility to completely throw that plan out the window, right? So you want to plan them to the priorities. You want to keep the crew members focused on what the priorities are at hand. But when we discover that seatbelt rock or we discover something new and exciting, we're going to throw the plan out the window. So anyways, just a couple points there.
Yeah, those are great thoughts. And yeah, it's heartening to hear that the engineering and the operations community recognizes that component of being flexible in plans, because that is very much what a field geologist does intrinsically when they go to the field. You always go to with a plan, but you're always ready to change that plan, perhaps entirely, even at the first outcropping visit. Let's see, who's next with a question?
We have Brian Turner next.
Brian Turner.
Yeah, you guys were talking about the bottleneck between the back room actually talking out to the astronauts, but doesn't that apply just if we start crowdsourcing information and getting all the number of scientists that want to work on lunar projects, filtering that down to the people who can make those decisions? We've all seen social media kind of lose its mind, you know, and the popularity of cat videos is a bit of a mystery. And so is there a methodology for bringing that massive amount of information that can be tapped into via crowdsourcing down to a level where we can see what really applies to our mission in the moon? Because we can do a lot more of that than we could ever do in 1969.
Yeah, I think that's a critical question. You know, we're going to be flooded with data coming back from the moon. And as you mentioned, we might be flooded with inputs coming from external to the science team. So how do we set up the science team to manage all that? I think there's a really big need there. Does anyone have any insight on that?
Yeah, crowdsourcing in science is strategic and decisions are tactical. You can provide a lot of input from a lot of people. That's great, but you don't do that real time. You have to focus it down. That's where the wired missions work. Like, we have strategic planning meetings, and, sometimes we are, I mean, it's I have to be careful because, like, what I consider tactical is really, a day behind strategically, right? For a true tactical day on the moon. So we have time to react. But if you think about that way, it's like we get data, we analyze it, and then we make a decision that's going to act operationally the next day. We are not real-time commanding, and I think it plays to the moon that you wouldn't want to do that either. You wouldn't want science to be constantly poking, hey, go pick up that rock. I mean, you could ask them to do that, but I think that becomes really tricky. I think of it more in terms of, like, you survey a site, the scientists talk, you use machine learning, you use crowdsourcing, whatever source you want, but that's used to develop a plan for the next day, not for the current tactical day. There's nothing so shiny on the day of an operation, I will posit, that is worth changing the goals of that day of operations. It's simply from a safety standpoint, right?
I'm actually talking about clear back to present day. Well before we ever set foot on the moon, getting that information up to the science people, not so much the astronauts.
Okay. Well, in that case, yeah, we do that all the time. I mean, so I think Jim Skinner from USGS pinged me from the National Center, pinged me about to note that the data products that it takes to make maps, for example, is a long and arduous process and requires a lot of people's eyes and labor to make that happen, so that we can make these maps. What I'm doing, what I would call tactically today, or super tactically today, like we found a result, and by the way, we need this thing, we need this mapped out, we need to know the buffer for the airfields. Okay, I can generate that number. But behind that was several years of developing that base map, there was the planning to make sure we were operating on the same agreed upon set of data and coordinate systems, and that requires a lot of people to develop first. And, and there was machine learning that went into rock detection to get the EDL, the intercept and landing, to work, for making the people figuring out which areas were hazardous, and then putting that into a map that then was actually fed into the rover when it landed. I mean, this is Perseverance was the first mission we actually put a map on the rover, and it made the decision based on the map that we provided. We scrubbed that map for years. We would have scrubbed it up to the day of the landing if we could, but we had to come up on agreement. So there's a lot of this quote unquote crowdsourcing, but really just information sourcing of lots of people to get these data sets ready for these missions, and so that you can make decisions on them.
Thank you.
Yeah, thanks. Okay, who's next with a hand up or a comment that's burning?
We have Miss Bahar. I'm sorry if I mispronounced that.
Oh, no, that's perfectly fine. Thank you very much. So it's basically Misbah. The UR is never pronounced, but that doesn't matter. The thing is, for me, coming from the flight operations as well, I think one thing that I see, because I've been involved in few analog missions, I see that we go to the analog missions and the focus is always a lot on the science thing. So we see that a lot. So when you bring the engineers there, you get sensitive to the science thing. But I think one thing that both Alex and Ernie mentioned before, I had raised my hand before. So anyways, I'm going to continue on that, is that I think it is very important that also the science people get to know the operations, because in the analog missions, we are never able to reflect all the constraints that we have, the flight rules, the instruments, all the things that the flight control team is monitoring, and the decisions they have to make based on those telemetries are never reflected properly in the analogs, at least the ones that I have seen. So I think it is very important also for the science team to get a flavor of the real-time operations and how the decisions are made. And unfortunately, I think it's a little bit difficult to implement that, because you can't really go with the full tools and with all the suits. Maybe we do at certain level, but at least not in the majority of the analogs. So I think the proposal there done to get like a real-time ISS EVA being analyzed and discussed to understand why flight control team is making certain decisions certain way, I think that is really, really important to make the other side sensitive to the operations and why we do operations in a particular way.
Great, thank you for that insight. I have a question, maybe to spur a little bit of conversation, unless there is there someone with a burning hands up question before I start?
Yeah, this is Dean, real quick.
Oh, please, Dean.
Miss Bahor's comment. The RATS 10 alumni in the audience will recognize what I'm saying, but we were able to do a lot of what he's talking about in RATS 10 because we had planned that to be as much an analog of understanding how to operate. But it was very expensive. It was very time consuming, and it ate a bunch of our lunch for about a year. It can be done in an analog mission, but it is not a simple thing. It is not 3 or 4 folks going out in the field. It's a marching army. So, but I still think we learn so much on RATS 10 that every once in a while something like that really needs to come together to learn these things and to get people exposed to the kinds of things he was talking about.
Great, thanks. The question I was going to ask sort of follows along with what we were just talking about. How do we best prepare sort of the scientists who will eventually populate this science team? How do we best prepare them to sort of sit in that chair on day one of that mission and be able to speak the language, work the tools, integrate with the operations? What sort of things do we need to do specifically? I'm hearing a lot about analog tests and training in the field. What other sorts of things are needed in order to educate a scientist to be essentially a sort of a mission operations person too?
Jose, if I can answer to that thing, I think in flight operations, we do like tons of simulations for flight operations that are really focused on the flight operations part. These are
okay, these are not in the field, but they're using the simulators and the data that we are seeing in the telemetry and responding to the malfunctions that are planned by the sim teams. And I think it might be very good for the science teams to attend some basic trainings where they understand the basic terminology, and then they can attend these sims to be a little bit more sensitive on the flight operations way of doing things a little. That will be my suggestion at least.
Great, thank you. Any other input on this line of conversation?
Yes, I'll add to that. So from
Yes.
a payload operations for ISS, there's a process in place where there's a training team that works with the scientist, teaches them how to use the tools and the protocols for real-time operations, puts them in simulations, when needed, trains them on how to actually speak to the crew and certifies them to be able to do that. So there's a process in place, at least for ISS. I fully anticipate the same thing will occur for Artemis missions. I don't think that's been fully developed yet, but I know folks are engaging in discussions on that.
Great, thank you. Okay, I think maybe we can.
Jose, if I could just add to that
please.
one, though.
Yes, absolutely.
Yeah, just as far as how to get them up to speed, it Sims is obviously a really good thing, but also part task training. Get the scientists into the part task trainers on the hardware, not necessarily on the instruments, but on the suits and on the other things that the crew is going to have to deal with while they're trying to do the science. That way the scientists have an idea what the crew's dealing with. The crew isn't just there thinking about the science. As Alex had said, and Dean has said, there's a whole lot of other things going on in their head. It's a very high-risk operation they're doing by being out there EVA. Make sure the scientists understand what are the limits of the consumables, what are the limits of the suits, and anything else that the crew might be dealing with. So get them to understand that, I think, is a key issue.
Yeah, I think that's really key. Basically get everybody to understand, their mindset and what their experience is going to be during mission. I understand that Pascal has been waiting to chime in. Are you there, Pascal?
Yeah. Hi, everybody. Good. How are you, Jose? It's very well run, by the way. Yeah, thanks.
Thanks.
I just wanted to make a comment because this has come up sort of tangentially throughout the day, but I expect the optimal ways of providing mission and specifically science ops support will and should evolve over time. And one significant delineation is between supporting sortie missions and fixed-based missions. Now, with Artemis, of course, we plan to set up an Artemis base camp, but ahead of that, we may have one or several sortie missions where we're not entirely sure we will be returning to that site that was visited on subsequent missions. And in some sense, the Apollo program was very luxurious in that regard, in that it really was not concerned about establishing a long-term foothold or setting up a base camp on the moon. It went to sites of scientific interest, that had burning science questions to them. And so we essentially sent crews for very short visits, of course, but they were sortie missions. And so therefore, the short time that each crew had at the surface of the moon had to be absolutely optimized. This is why, of course, you sort of plan down to the minute the EVAs. You essentially never return to the same location twice. You have a very orchestrated approach to collecting your samples, to making your observations. And of course, at some level, you still have some tactical decision making left to the crew, but both strategically and tactically, a lot was decided ahead of time, planned ahead of time, and done with the benefit of an entire science backroom. That's sortie missions. Now, we might start off with that on Artemis, but very quickly we will be evolving towards a fixed base approach to doing our field exploration. And the patterns of exploration are quite different when you all of a sudden are stuck with a fixed base. So the big advantage of a fixed base, of course, is now you have an infrastructure on site. You might have more vehicles, including pressurized rovers, places to park them. You have assets. Now you have a fixed base. But then you are at the same time no longer visiting a brand new site sort of you know, in a different corner of the moon on every mission. You're now entering a different mode of exploration. We've had that experience up in the Arctic with the Houghton Mars project, where we've set up a base camp, and from there, over the summer seasons, we've been roaming around. And of course, at first you treat each outing as a sortie mission, but over time you realize your patterns of exploration are as follows. You will identify relatively quickly, early in your mission, some sites that are very, very rich scientifically. And so an optimal exploration plan, for example, will not require you to spend necessarily the same amount of time on every pixel of your map. But instead, you identify these sites that are particularly interesting. They could be outcrops, they could be ejecta blocks, they could be just sources of whatever information you're after. And you will notice that day after day, week after week, season after season, year after year, you will be returning to these very rich sites, and they will still be yielding very interesting samples, a lot of good work, part of which can be done in situ with a lab on site now that you have a base. Part of it will be done by bringing the samples back to the Earth. But the point here is that the way you will support that kind of science and the way we are trying to set ourselves up to support Artemis really should be approached with flexibility in mind. That was brought up earlier today, but with sort of an evolutionary path in mind as well. We're going to be picking up where we left things with Apollo 17, with a geologist PI essentially on site, to something that will eventually become a fixed-based operation of an exploration of the moon, maybe with still the luxury of a few sortie missions every now and then to you know, far remote places, but we should have a mission support structure that is expected to evolve over time and be adaptable. And I think that will be the key thing to sort of allow.
Yeah, thanks, Pascal. I think that's really important. I think we have a question from the chat that we want to get to.
Yes. So a few minutes ago, Catherine Logan, if you're still here, we'll ask the question, has there been any effort towards mapping regolith geology? So there are probably a couple geologists here in the conversation, so I just wanted to see if anyone could give some input here on that. I'm pretty sure that we have had some lunar maps, so the USGS has been involved in this process, and I'm not sure how much detail we're thinking about here with this question, but I have seen some lunar geologic maps. I'm not particularly certain for mapping regolith in this context.
So the reason I was asking that is from an implementation viewpoint, and using the lunar regolith for habitats or building whatever, but the chemistry would need to be known in order to do that. So then the landings could be controlled as far as any need to get any kind of building regolith. So no detail particularly, but anything that's available. I know geological surveys on Earth are very useful. So it would seem to be useful on the planets as well.
Thanks for that question. I think that speaks to maybe a sort of a high-level need that would be needed for a science team to be effective, and that's to get as much situational awareness about the exploration site ahead of time. So compiling things like maps and orbital data in a way that is easily accessible and useful and interrogatable by the science team. So I think data systems, tool development in that sense, I think that fits in that category. All right, and any other inputs? We have just about 7 or 8 minutes left. We haven't spoken too much about traverse planning and some of these other possible topics that we could talk about. I don't want to derail this conversation because I think we've got a lot of really good input. But anyone else have any insights at all about any of these questions, or have another question they want to bring up?
Yeah, this is Dean. Real quick,
Yeah,
to your how to get everybody embedded and things like that. You know, when Apollo did their crew geologic training, there were really 3 phases. One was, for lack of a better phrase, show and tell, which was pretty much one way from the geologists to the crew members. Then there were the let's go out and practice doing a traverse. Let's start talking about how you do what you do when you get to the moon. But the last phase, which was what I'm thinking about, was when they did joint integrated sims, which was kind of the last part of the training before they flew. And what's often not recognized is that the joint integrated sims included the people that would be talking to the crew on the moon. So the Capcoms were working as part of the sim. So what you were really doing there was training not only the astronauts, but you were also training the people that would work with the crew members on the field, because they were the same bunch. So that really worked well. By the time the control team, including the Capcoms, got with the guys on the surface, they all knew how to work with each other because they'd done so much of that. So the point is that your field ops aren't just let's go do geology. A lot of your field op is let's everybody learn how to do what we're doing in a real life simulation, a joint integrated sim like they did on Apollo.
Yeah, thanks, Dean. I think that's really important. Get everybody familiar with one another and also with what each other's jobs is. I think that's going to make things really run smoothly. All right, anybody else?
I was just going to add to Dean's. We're actually planning that the Capcom be one of the crew members that's trained right beside as a backup crew member to the Artemis missions, and that will help twofold. One, it will help make sure that the crew and the scientists and the Capcom and the flight control team are all synced up from the very beginning of training, but it also allow us to really push the science emphasis on that Capcom, because you want him, as well as the crew members, to have that autonomy that we keep coming back to make those smart real-time decisions and be able to identify samples and characteristics of the terrain and be able to do real-time traverse planning. And they will be an expert just like the crew members on the lunar surface.
Yeah, the other thing about the Capcom is that they can serve as they're your crew members buffer between people who don't understand what the crew is actually having to do and the crew themselves. So if you read the Apollo transcripts in the ALSJ, for instance, particularly on 17, you often see how Bob Parker is acting as a filter between the back room and the guys on the ground, so that the guys on the ground guys on the moon don't get overloaded with stuff. And that again came from that very close knit training that they did. So that's great you're thinking about that.
Yeah, I'm actually a certified Capcom as well, and you're right. You are the crew's representative in that control room, and so you're always fighting not only from a risk standpoint, but also from an emotional standpoint, and making sure that you filter that emotion from either the flight control team up or from the crew down. And so, good points, Dean.
Yeah, that's great stuff. Yes.
In complete concurrence with what Dean said, one of the things that I hope to highlight in my talk earlier was the need to speak a common language and have shared objectives. And if you go to the link that's in my abstract, and the one for Apollo 17 and the discovery of the orange soil, the aspect of trust and full communication among the science support people and the crew on the ground and Capcom, the three-way interactions there, all of those people had been in the field together. And that brief bit of the video that is linked there gives you a fine example of how it can work. Trust the geologist on the ground, Schmidt, give him his head, communicate in all directions, but don't be so rigidly locked down on a script, on a timeline script, that that the science suffers. And this is in concurrence with what you said, Dean. Thank you.
Thanks, Pat. I think we have another hand up.
Yeah, Jose, it's me, Mispa, once again. I just wanted to get Alex's opinion on this thing. So basically, I mean, we can kill the concept of having a SciComm based on whatever I'm hearing. I think looks like that we are going to be going with the concept of Capcom, basically doing all the communications. And this discussion that we had before of having a SciComm separately, doing a conversation on the science operations, I think that is probably not going to be. Is that the impression that we have? It makes sense to me. I just want to make sure that this is the understanding of the community as well.
So I will never, ever, say that's not going to happen. I think that there is a lot of validity in the SciComm position. But we are doing current testing, and while SciComm has been tested at length, at a little at RATS and a lot at NEMO, there were some critical elements missing in that. And as we've started testing that again, we are realizing maybe rather than having the separate entity talk to the crew members, that you just make that Capcom that smart person. And in reality, we actually have two people sit that Capcom position. One is called Capcom, one is called Ground IV, and that's the person that's really talking to the crew members during EVAs, and they are so familiar with the EVA task, and we would expect to make them a science expert to the level of a grad level discussion. I know Jose's familiar with the plans, and Lauren and Kelsey and Trevor are developing this training session to really get that person up to speed. And the most important part that we're learning is that if we get tension, and this happened during Apollo, if we get that tension between Capcom, SciComm, safety and science, operations and engineering at the high level, it doesn't go well. But if it's integrated at a lower level and with a consensus and recommendation, it often goes a lot smoother. And we have that. I mean, we do that all the time on ISS EVAs. Someone was like saying, "Oh, they're all rote," but they're not. I can't tell you an ISS EVA where there weren't at least 4 or 5 failures, and we had to go off script and figure out how to fix the failures. So let's not say we're never going to use the SciComm, especially when we maybe move to a more autonomous, sustained lunar presence. It may come back. It's just that so far our testing right now shows that it's that having an expert scientist, field scientist, be that ground IV Capcom role is actually a lot more efficient and a better way of communicating to the crew.
Great, thanks for that.
Yeah, real quick, Bob Parker was the Capcom on 17. Bob was a physicist. Joe Allen was the Capcom on 15. When I say Capcom on 15, when they were the guys that were talking to the crew when they were on EVA, he was a physicist. Tony England did it, who was a geophysicist. So the point is, you could have called those guys a SciComm and not been inaccurate, but the point is that they were still Capcom. And when we did this on RATS, we actually had a Capcom and a SciComm, and when we were doing ops, the SciComm was out of the loop, and when we were doing science, the Capcom was out of the loop, wasn't the one talking. So there's many ways to skin this cat, and I think you guys are talking about the right things to be done, and it really comes down to what's the easiest way to do it.
And if I can just add on what Alex and Dean have just mentioned.
Yeah, go ahead.
Yeah, so I would say that just the one thing to keep in mind too would probably be the complexity of the task and the amount of variety of tasks simultaneously occurring as to whether or not you would want a simultaneous Capcom and SciComm. With a small crew complement, a single Capcom, I could be fine, but with larger crew complements, such as like with the ISS, you have payload ops going on simultaneous with other tasks, then it may come into consideration. I don't disagree with anything that's been said, just that, as the evolution of missions and task complexity go, it could change, it could evolve. Something to keep in mind.
Great stuff. All right. Well, sadly, our hour has passed. I really thank everybody for their contribution. I think we had a great conversation. I think my screen is still being shared, but this slide just sort of has my high-level sort of thoughts and of what I've heard so far. It seems like tool development of various kinds is sort of at the top of the list as far as tools that are going to allow the science team to engage with data. And then there's sort of people building, I guess, is probably one way to say it. Getting teams together from the operations, engineering, science, talking early on in the field, in simulations, in sort of real world situations, to build things like the same language, understanding each other's job, and I like what Pat said about building trust. I think those are going to be really key. Any final thoughts from anybody in the room before we end?
One of the things, this is Dean Epler again, one of the things that's always been impressive to me in Apollo, specifically with Jack Schmidt, is that Jack came into the astronaut office as a geologist, but he didn't lean on that and say, I'm only a geologist. You find Jack, you find threads of Jack in engineering meetings and science meetings and computer, programming meetings and ops meetings. Jack earned his spot on Apollo 17 by being tremendously versatile, and he's often the only scientist astronaut you see down on the floor of mission control, particularly on missions like Apollo 11. The bottom line is that this is, particularly for folks that are interested in becoming astronauts in the middle of this mix, is this isn't about being a scientist that gets ferried to the moon and then does your stuff. This is, all kinds of people doing all kinds of things that may have very little to do with what their academic degrees are in. And that's what made Apollo work. And that's, in my opinion, why Jack ended up being the geologist that worked on the moon when none of the other scientist astronauts flew on Apollo.
Those are great parting words, Dean. Well, thanks again to everybody. We are taking more complete notes than what's on this slide, and we'll have a summary of this breakout and also the other breakout that's going along concurrently tomorrow morning when we all reconvene on WebEx at 11 o'clock. All right, well, thanks everybody again, and enjoy the rest of your day, and I look forward to seeing everybody tomorrow and talking again at our breakout. Thanks.
Thank you, Jose.
Thanks,
and Kelsey.
Bye, Pat. Bye, Dean.